So there's looks like there's quite a lot going on in this question. We'll take it one stage at a time, work out what information we're given and what we should be doing with it. So let's start. The lifetime of batteries is normally distributed with a mean of 150 and a standard deviation of 25. So let's quickly note that down. So if X is, this is the lifetime of a battery, will be modelled by this normal distribution. So a quick sketch would also be useful. The usual normal distribution shape with a mean of 150. And we could write the distribution there. 150 is the mean and the variance would be 25 squared. So that's the lifetime of a battery. Then a box comes in. We've got a box of 12 batteries. So we've got a sample size. This is probably heading towards binomial now. Find the expected number of these batteries that have a lifetime of more than 160. So this is a new variable. This is y. It's counting the number of batteries. Number of batteries out of 12, because that's our sample size. Number of batteries out of 12 that have a lifetime of more than 160 hours. Okay, so X was the lifetime of a battery. That's the normal distribution we've drawn. But Y is saying, in a sample of 12, how many of those batteries have a life longer than 160 hours? So this is clearly a binomial situation, because there's 12 things, 12 batteries, and we're asking whether each one has a life greater than 160 or not. So BNP, but what we're missing here is the value for P. And P must represent, you look at the property at the end, we want a life greater than 160. So P represents what is the probability of a single battery having a life greater than 160 hours. And that's where we have to go back up to this normal distribution. So let's label 160 on there. What is the probability of a battery having a life greater than 160? So you're going to need to do a normal CD on your calculator. It asks you all the questions. Sigma is 25, mu is 150, lower is 160, and upper you just put in a big number, put in 10,000 or something, and see what probability comes out, and it should be 0.3446. If we keep 4 decimal places there at least, so that we're more accurate. Okay, so we've had a normal distribution and a binomial distribution. What's the actual question? Find the expected number of these batteries that have a lifetime. So the actual question is, what's the expected value of Y, the expected number of batteries out of 12? Well, it's a binomial distribution, so the expectation is just n times p. So you've got 12 times that probability. Multiply those together and you get 4.13 to 3SF. Now that is a number of batteries, so it's strange that it's a decimal, but it's only an expected number. It's an average, it's a mean, so it's perfectly fine that that is a decimal. Okay, so far so good. Let's read on. We've got a new situation. We've got a company Y, so it's unfortunate I've used the letter Y once. We're going to have to restart Y. Batteries sold by company Y are normally distributed with a mean 160, so that's a bit higher, and 80% of them have a lifetime of less than 180 hours. So let's start to think about this distribution for Y. We've got a normal distribution again. We've got a mean of 160 this time. But the question doesn't tell us the variance. So we're going to need what I call the underworld, the Z distribution, to figure out the variance. If you don't know the mean or you don't know the variance, you need to go down to the Z distribution. But we are told something. We're told that 80% of these batteries, let's just highlight the question, 80% of the batteries have a lifetime less than 180. So I can show that on the diagram. If I put 180 up here, this area represents 80%, so 0.8 is the probability of being in that region. Okay, so I'm just going to put a clear dividing line across. This is not the binomial we're looking at at all before. This is the lifetime of batteries from company Y. Underneath, we'll put our underworld, the Z distribution in. Remember, that's always centered on 0. So Z is a normal distribution, mean 0, variance 1 squared. There's going to be a Z value there that we want to try and find out because they pair up. Remember, the X value and the Z value underneath it pair up. The area is still 0.8. So down in the underworld, we can do an inverse normal calculation where sigma is 1, mu is 0. The area to the left is 0.8. And the calculator should give you a Z value there of 0.8416. Z equals 0.8416. You might even keep more decimal places if you want to. So we're ready to put all the data we have into the formula. Remember, the standard formula here is X equals mu plus Z sigma. X is the value from the real life distribution, that's the 180. Mu is the mean of the real life distribution, that's 160. Z is the Z value that corresponds with 180, the one that matches underneath, the one we've just calculated as 0.84162. And sigma is the unknown in this equation, so you can quickly rearrange that and solve it to get sigma equals 23.8 hours to 3 significant figures. Remember, 3 significant figures is always good in statistics. Okay, so let's label that we've done part A, and down here is where we started part B, which we've just finished. Let's read on. There's a new bit and plot. Both companies sell their batteries for the same price. Which would you recommend? Give reasons for your answers. So this decision has to be based on numerical evidence that we've already got. So we're going to do a quick summary. We've got batteries from X and we've got batteries from Y. We don't know much numerical information, but we know the mean. The mean for X was 150, but the mean for Y was 160. So Y seems better. The standard deviation for X was 25, and we've just found out that the standard deviation for Y is 23.8. So I would recommend company Y for 2 reasons. Their mean life is longer because that 160 is greater than 150, and they are more consistent, slightly more consistent, because 23.8 is smaller than 25. Remember, sigma measures the variation, the spread in the data. So the smaller the number, the smaller the value of sigma, the less variation there is. So company Y's batteries will be a bit more consistent in their lifetimes, whereas company X's will be slightly more unpredictable. So there we go. The mark scheme doesn't actually bring that point in. It just says that company Y has a longer mean life. The mark scheme says that the sigmas are roughly equal to each other, so it's not worth comparing those.